Okay, this little discussion is going to cover the precise definition of a limit. The previous discussion talked about limits in layman's terms. We're going to try to get a little bit more mathematically rigorous here. So try not to bog down in it. But we're going to cover the precise definition of a limit. To do that, we're going to think about a function that is defined for all values on some interval except at possibly one value. So we have an interval that it contains the number a. We have an interval of x values. We'll call that interval I, but it's just an interval of x values, like say from 0 to a. And it contains some special number that could be 2. And f is a function that's defined for all those values from 0 to 8, all the values on I, except at one value, such like 2. Okay, so we've got a function f that's defined on an interval, except possibly at a. Then, the limit of f of x, here's the precise definition of the limit here. The limit of f of x as x approaches a, denoted with this symbol here, limit underscript x approaches a of f of x, is defined as a number, the number L. If for every positive real number epsilon, there is a corresponding positive number delta, such that the distance between x and a is less than delta, implies that the distance between the function and L is less than epsilon. Okay, now this is epsilon, this is delta. Traditionally in mathematics, when we're talking about small numbers that are positive, small positive numbers, we use epsilon and delta. But for our purposes, epsilon and delta are just arbitrarily positive numbers. And the strict definition says that the distance between x and a is smaller than delta, then that implies that the distance between f of x and L is smaller than epsilon, and that there's some delta for every epsilon chosen. Let's put that definition to work. Let's say we want to verify a particular limit. Now, up until now, to verify this limit, this is a continuous function, so we can just plug 2 in and we would get 4, and so we would say the limit is equal to 4 by direct substitution. That's how we calculate limits. If the expression is continuous, we just use direct substitution. But this problem says use the precise definition of a limit to verify that this limit is true. Okay? Before we do that, let's get some symbols down. NTS stands for need to show. This symbol means there exists. This smaller backward E symbol means such that. Okay. If we're going to use the precise definition of a limit to verify this, we need to recall that there exists some delta that's positive, corresponding to some epsilon that's positive, such that this expression implies this expression. That's what the definition says. The definition says that there exists some delta that's positive that corresponds to any arbitrary positive epsilon, such that this expression implies this inequality. This inequality implies this inequality. Okay? So, that means that we need to show that there exists some delta that's positive, such that x minus 2 absolute value of that is less than our delta, implies our function, which was x to the fourth minus 2x cubed plus x squared, minus the limit 4. Remember we said the limit was equal to 4. We're trying to verify that the limit is 4 when x approaches an a value 2. Will be less than any arbitrary epsilon. That's what we need to show right there. Okay. Well, what if delta was greater than 0, so that it's positive, but less than or equal to an arbitrary choice for epsilon divided by x cubed plus x plus 2. So wow, where'd you get that? Well, it'll probably become evident as I work further where this came from, but this is a factor of the polynomial. It's a cubic factor that divides evenly into this polynomial. Okay? What if delta was this arbitrary number? Well, let's see if that will imply that if x minus 2 absolute value is less than this choice for delta. Let's see if that would imply this over here. If it does, we're finished. Okay, well, let's take the absolute value of x minus 2 and set it less than this number. Dropping the absolute value bars, we have this. Okay. Now we can't multiply. It's probably important to notice that this expression x cubed plus x plus 2 is positive for any choice of x that's close to 2, and that's what we're worried about. We're worried about when x approaches 2. So, like for instance, if we were to put in 2, this expression would be equal to 12. If you were to put in 1, let's see, it'd be equal to 4. If you were to put in a number like 1.9, it'd still be positive, or 2.1, it'd still be positive. So this expression is positive, at least for where we're interested. So, since it's positive, I can multiply through this inequality without having to flip my inequality symbol. So I'm going to multiply through this inequality by that denominator to get negative epsilon less than x minus 2 times my denominator, x cubed plus x plus 2, which is less than epsilon. And I don't have to flip my inequalities because this is positive for all x values near 2. Now, this times this gives me this polynomial here. That's why I chose this, is because I knew it was this cubic was a factor of this polynomial inside the absolute value bars there. So I know that x minus 2 times this, and if you want to verify that, you can get out some scratch paper and multiply x minus 2 times this cubic, and you will get x to the fourth minus 2x cubed plus x squared minus 4. Well, I have this polynomial less than epsilon, but greater than negative epsilon, so I can now write that as an absolute value expression. And we notice, oh, here's our function, and there's our limit value. And so indeed, if delta is some number that's equal to or smaller than this, then the distance between the function and 4 will be less than any arbitrary choice of epsilon. So we're finished.